this tutorial where I'll be going through the paper that was written by candidates in the year 2023. Alright, my first question says figure 1.1 shows a solid cylinder of length 5 centimeter and mass 215 grams placed between two wooden blocks and a roof in order to determine the diameter of the cylinder. Alright, and the first question says state the diameter of the cylinder. Alright, the diameter of the cylinder can be calculated very easily by simply finding the length difference between these 2 points here. So between these 2 points of the wooden block. So here the last reading there is a value of 6.5 minus the first reading here, which is 3.5. So if you check, that's 3.5. So you have a diameter of 3.0 centimeter. Alright, and that's how I answer it. Number 2, suggest one possible source of error when taking the measurements. Okay, one source of error that may arise when you're taking measurements is what we call parallax error. Parallax error arises when you incorrectly place your eye. So when the position of the eye is incorrect, let's say you place it at an angle like this, okay, and you're measuring something that is here. So if you do this, you're most likely to encounter parallax error. So to avoid parallax error, you should place your eye directly above what you're measuring. Okay, so if you do this, you're least likely to be affected by parallax error. Okay, question B, calculate the number 1 volume of the cylinder. Alright, to calculate the volume of the cylinder, we simply use this formula. V is equal to pi r squared h. Okay. Alright, we're given much data here. We have the h as being 5. Okay, then we have the r as being okay. So let's calculate the r. So we know 2r is equal to the diameter. So 2r is equal to the diameter we calculated it to be 3. So if you divide 0 out by 2, we'll get a value of the radius as being 1.5 centimeter. So meaning my radius is 1.5 centimeter. And the value of pi I'm already given in the question. It's 22/7. Okay. So here I say the formula is pi r squared h. Pi is 22/7, the r is 1.5, and the h is 5. If you do your basic calculation there, you get a value of roughly 35.36 centimeter cube. Okay. Question B2, density of the cylinder. Remember, density is equal to mass over volume. Okay. So are we given the mass? Yes, they're saying the mass is 215 grams. Okay. So meaning our density rho will be equal to mass over volume, right? So the mass is 215, and my earlier calculation of the volume was that it is 35.336. Okay. So if I do my calculation here, I'm getting a value of roughly 6.1 grams per centimeter cube. So that's my intensity. Okay. Question 2. A 0.5 kg ball is released and falls vertically through a height of 10 meters and hits a concrete base on the ground. On hitting the base, the ball bounces back upwards but only covers 6 meters up. Number 1. State one characteristic of the motion of the ball as it falls freely. So here I wrote my answer to be that throughout the motion of the ball, its acceleration was a constant value. And this is true because for free fall, when a body is falling under the influence of gravity, its acceleration at any point is a constant value of 10 meters per second squared. Question B. On hitting the concrete base, calculate the ball's number 1 energy of impact. Okay. Alright, so let's have a simple diagrammatic representation. So we have a ball there. So it falls until it falls like that through a distance of 10 meters. So here to calculate the energy, we can use the formula that says GPE is equal to mgh. Okay, so the m, which is the mass of the ball, is 0.5. G is a constant value of 10, and the height that the ball fell through was 10. So in doing so, I'll get my value of 50 joules. Okay. Number 2, velocity on impact. Remember, when a body is falling freely under the influence of gravity, mgh, okay, GPE is equal to the kinetic energy of the ball. So we calculated GPE, which is the gravitational potential energy, to be equal to 50 joules. It means that the kinetic energy of the ball was also 50 joules. So we can use this data to find the velocity. So we're saying KE is equal to mv squared, right, over 2. KE is 50. M, which is the mass, from the question we are told is 0.5. V, we don't know, over 2. So we'll have here, let me write it over here. So we'll have 100 equal to 0.5 v squared. If we divide throughout there by 0.5 and there by 0.5, I'll have v2 is equal to 200. Okay, so v is equal to the square root of 200, which is approximately 14.14 meters per second. So meaning this was the velocity on impact. If you don't like this formula, you can also use this one. V is equal to 2gh. Okay, the height we're given it's 10. So we simply say V is equal to 2gh like that. So we'll have 2 times g is 10, the height is 10. Okay, so we'll have 200 there and 14.14 meters per second. So if you don't like the earlier formula, you can also use this one as well. Now, question C. Explain why the ball did not reach terminal velocity when it's downward and during its downward motion. Okay, so here my answer was that because it did not fall long enough for the weight of the ball to equal the drag force. Remember, when a body is falling through the air resistance that the body experiences increases as the speed of the body increases. So there reaches a time where the weight of this ball is equal to the air resistance. And in other books, the air resistance is sometimes referred to as the drag force. So when this happens, a body is said to reach terminal velocity. However, we are told that the ball did not reach terminal velocity during its motion. So this is probably because the ball did not fall long enough for the weight of the ball to equal the drag force. Okay. Question B. The ball could not cover the height of 10 meters when bouncing back. So this is very simple. The reason why the ball could not cover the initial height of 10 meters, but rather it covered a height of 6 meters, meaning that it lost energy. So here our answer would be that the ball lost energy upon collision with the ground. So there was an energy transfer in the form of heat and sound. Okay, so I presented my answer to be that because the ball lost energy upon collision with the ground in the form of heat and sound energy. Alright, question 3. Figure 3.1 shows a body of mass pulled by a force of 150 Newton at an angle of 60 degrees to the horizontal. A says, on figure 3.1, indicate the direction. Number 1, the direction of friction force. Remember, the body is going this side, and we know that friction force always acts in a direction that opposes the motion of the body. So it will be in this direction here. So this will be the direction of friction. And number 2, weight. Okay, weight is the force that is due to gravity, and we know that gravity tries to pull bodies towards the center of the earth, towards the ground. So the direction of weight will be downwards like this. So this is the direction of weight. All right, B says calculate the force. Calculate the number one. Calculate the number 1 force that pulls the body in the horizontal direction. Okay, so this means we should calculate the force that pulls the body in this direction here, and let's call this force X. Okay, so to calculate this, we'll apply a little bit of trigonometry. So we know the angle that is acting in between here is 60 degrees, and the size of the force here is 150 Newton. Okay, so we'll use this famous Socator. Okay, so this side here, the one that we want is what we call the adjacent, and here is the hypotenuse. The hypotenuse is there, and this part here is what we call the opposite. Okay, so we want to find the value of the adjacent, this value here. So to find the value of the adjacent, we'll focus on this part here, the graph. So we have cos, adjacent, and hypotenuse. So we have cos theta is equal to the adjacent over the hypotenuse. Cos theta here, the theta is 60 degrees, is equal to the adjacent, that's what we want, and we are representing it with the letter x, over the hypotenuse, which is a value of 150. So if we like multiply this and that, we'll have x being equal to 75 Newton. Okay, so the size of the horizontal force was 75 Newton. Okay, question 2, acceleration of the body as it is being pulled. Remember this formula, force is equal to ma. So we want acceleration, so we rearrange the formula to be that acceleration is equal to force over mass. We have the force. Do we have the mass? Let me check. Okay, here we have body of mass 60 kg. Okay, Right. So here, A is equal to F over M. F is 75, the mass is 60. So here I'm getting a value of 1.25 meters per second squared. So this is the value of the acceleration. Okay. Question 4. A bird emits high-pitched sound to enable it to navigate its way around barriers. A says define pitch. So my definition was that pitch is the measure of how high or low a sound wave is. And you should know this for a fact that pitch is directly related to the frequency of a wave. Okay. Question B. Explain the relationship between the frequency and the high pitch of the sound produced by the bird. So, like I was saying, the high pitch of the sound produced by the bird is directly proportional to the frequency of the sound wave. Okay, meaning that the higher the pitch, the higher the frequency, and the lower the pitch, the lower the frequency of a sound wave. Question C. After emitting such a sound, a bird receives an echo from a barrier after 0.02 seconds. Take the speed of sound in air as 340 meters per second. Calculate the distance between the bird and the barrier. Okay, so let's have a representation here. So suppose the bird is here. Okay, I'll represent the bird in form of a human. So for the echo, for the bird to detect the echo needs to travel twice the distance. So we'll have the formula speed is equal to 2d over time. So we want the value of d. So we will rearrange this to be s times t over 2. The speed is 340. The time we're told is 0.02 over 2. So this will give me a value of 340 times 0.02. Okay, times 2. So this will give me a value of 3.4 meters. The wavelength of such a sound wave, if its frequency is 100,000 hertz. Okay, remember this wave equation. V is equal to frequency multiplied by the wavelength, which is denoted by this Greek symbol that is called lambda. Okay, so we want the wavelength, so we rearrange the formula to be wavelength is equal to V over F. So the value of V from the question is 340, and F is the frequency we are told it's 100,000. Okay, so if I divide this, I'm getting a value of, let me put it in scientific notation, I'm getting a value of 3.4 times 10 to the power negative 3. Take this away, meters. So this is my wavelength. Alright, question 5. Elena hangs a jersey on a line after washing. The learner recorded the mass of the wet jersey before hanging it on the line. A says state one environmental condition that would enable the jersey to dry faster. Okay, so the reason why the jersey is like drying fast is because of the process of evaporation, which is basically the change of state from liquid to gas, and this gas is in the form of water vapor. Okay, So one environmental factor that increases the rate of evaporation is the presence of wind. Eh, and another factor that we can write that increases the rate of evaporation is high temperature. So we can also say here high temperature. Okay. Question B. After 1 hour, 200 grams of water had evaporated from the jersey. Assuming the assuming that the water evaporated due to only heat absorbed by the jersey and taking the specific latent heat of vaporization of water as 2300 joules per gram, calculate the number one amount of heat absorbed by the water in the jersey in 1 hour. Okay, so to calculate the amount of heat that is absorbed by the J's in an hour, we'll use this formula. Q is equal to LV multiplied by M. Q represents the heat energy. LV represents the specific latent heat of vaporization, and M represents the mass of the water. So if we substitute, we'll have 2300 multiplied by M, which is 200 grams here. Okay, so since all the units are the same, all of them are in grams, there's no need of converting them to kg. So here we just go directly. So I'm getting a value of 4.6 times 10 to the power 5 joules. Okay. Then number 2 says rate at which the jersey absorbs the heat energy to enable the water molecules to evaporate. So this question is indirectly asking us to calculate the power, because the definition of power is that it is the rate at which work is done. So here we'll use the formula that says power is equal to work over time. Okay, so what's my time? My time is 1 hour. Okay, so all right. Okay, let me put it like this. So we have P is equal to W over T, and my work, which is same as energy, is equal to 4.6 times 10 to the power 5, the one that I earlier calculated. And my time, since I'm told 1 hour, I know that 1 hour, if I convert it to the SI units, which are seconds, will give me 3,600 seconds. So I'll substitute 3,600 seconds there. So doing so, I'll get a value of 1.2778 times 10 power 2. So if I approximate this, I'll have 1.28 times 10 power 2 watts. So this was the power. Says figure 6.1 shows mirrors at right angles with each other. A ray of light in the vertical plane B strikes mirror 1 as shown. And the question says calculate the angle of refraction R for the ray after striking mirror 1. Okay, so for us to calculate the value of this R here, we'll have to apply a little bit of trigonometry. We know this entire part here is 90 degrees. So if we can somehow find the angle that I've drawn there, then subtract it from 90 degrees, then it means we have gotten the value of R. So to do this, we'll use tan theta remember tan theta, if we say this our theta here, is equal to opposite, opposite, opposite over the adjacent. Okay, the opposite value is 3, the adjacent is 2.7 tan theta. So then if I say theta is equal to, okay, let me punch this on my calculator. So tan inverse, so this is giving me a value of approximately 48.0 degrees, meaning that let me erase this, meaning that the angle here from there to there is equal to 48 degrees. So if I say R is equal to 90 degrees minus 48 degrees, I'm getting a value of 42 degrees, meaning that this R here is 42 degrees. Okay. The second question says, calculate the angle of incidence of the ray when it strikes mirror 2. Okay. So mirror 2 is here on this side. Okay. So the angle of incidence that they are talking about is this line here. I'll present it with that. Okay. So let's draw how its normal is going to be. So the normal will be like that, and the reflected ray when the incident ray strikes mirror 2 will be something like that. So this will be our reflected ray, and here this is the angle of incidence that they want us to calculate. However, this will be extremely simple because we know that we know the value of this R here to be 48 degrees, and we know here we know this angle that is formed between these two lines here is a 90 degrees. Okay, so simply say 90 degrees minus 48 degrees. So this will give me a value of 42 degrees. Thus, my angle of incidence is 42 degrees. Question 7. Figure 7.1 shows the current to voltage graph for a filament lamp. Right. The first question says, state the range of voltages where the resistance of the lamp is constant. Okay, the resistance of the lamp is constant where before the curve starts to bend. So okay, so this is a range of from 0, so we're saying from 0V to 2V. So this is where the resistance is constant. Okay, after it starts bending, the resistance no longer becomes constant because the graph does not obey what we call Ohm's law. Okay. Question B, at the operating voltage of 4.0 volts, calculate the resistance of the lamp. Remember, resistance is given by the formula R is equal to V over I. So we simply go to where the voltage is 4. Okay. Right. So where the voltage is 4. Okay, sorry. So we have this. Okay. So where the voltage is 4, the value of the current is 0.3. So we'll substitute here. So we'll say 4 over 0.3. This will give me a value of approximately 13.3 ohms. Question C. The filament lamp is connected in the circuit shown in figure 7.2. A charge of 240 coulomb flows through the lamp for 10 minutes after the switch is closed. Calculate the number one current through the lamp. Okay. Given given charge given charge and time, we can use this formula that says current I is equal to Q over T. Q represents the charge. Okay, then the charge is 240. Let me take this there. So the charge is 240 and the time is 10 minutes. However, the time should not be in minutes, but rather it should be in seconds. So we should multiply it by 60. So this will give me a value of 600. If I do my calculation here, I'm getting a current of 0.4 amperes. Okay. Number two, energy used by the lamp. Okay, remember this formula. Sorry, energy is equal to Q times V. Right. We have the value of Q as 240, but we don't have V. Okay, but since we calculated the value of current and this part here to be 0.4, we can simply go to the graph and check the value of voltage when current is 0.4. So we'll see that from the graph, when current is 0.4, the value of voltage is 12 volts. Okay, so meaning the voltage is 12. Okay, so here we say energy is equal to Q times V. Q is 240 and V is 12. So this will give me a value of this 2880 joules. Number three, number of electrons that flow through the lamp in 10 minutes, given that one coulomb of charge contains 6.24 times 10 to the power 18 electrons. Okay, this value here, it's not scientifically correct because the charge of an electron is actually 1.6 times 10 to the power 19 coulomb there. So I'm sure there was a likely mistake. So I'll use this value here to calculate. Remember, Q is equal to N E there, where N represents the number of electrons and this E minus and this E with a minus represents the charge of an electron. So if I make the N the subject, I'll have Q over E minus like that. So my Q was 240, then my charge of an electron is a value of 1.6 times 10 to the power 19 there. If I do my calculation here, I should get a value of roughly 1.5 times 10 power 21 as my number of electrons. Okay. Question 8 says, figure 8.1 shows a circuit symbol of an electronic component. Name the component. So this component is what we call a diode. Question 2, suggest the function of the component. So the function of this electrical component called a diode is simply to ensure that the flow of current is in one direction only. So it ensures that current flows in this direction here, which is called the forward bias. So it ensures that current flows in the forward bias direction. So here I presented my answer to be that it ensures that the current flows, the flow of current is in one direction only. Okay. Question B. The component is connected in a circuit having a battery of EMF 6 volt and a 1.8 coulomb a 1.8 ohm resistor as shown in figure 8.2. On figure 8.2, draw an arrow to indicate the direction of flow of current in the circuit. Okay, the direction of flow of current in the circuit is in this way here. So it is in this way. Okay. Then number 2 says calculate the current through the lamp. Remember, current is voltage over resistance. The voltage is 6 volts and the resistance is 1.8. 6 divided 1.8 gives me a recurring number of 3.3333, which I can basically approximate to be 3.33 ohm, like this. So the point is in between there. Okay. Then question 3 says explain what happens to the current flowing through the ammeter when the terminals of the battery are reversed. So when you reverse the terminals of the battery, remember current flows from the positive terminal from this direction to the negative terminal. Okay, so if you reverse the polarity, it means that the current, the ammeter reading here will not register any reading at all. It will be zero. Why? Because there will be no current that would be flowing when the direction of current is in this way. Because in this direction, this diode here has what we call infinite resistance, so it will not allow the flow of current through it. Okay, so the ammeter will register a 0 amp reading. Okay, so I presented my answer to say the current flow through the ammeter decreases to 0 because the diode completely blocks flow of charge in the reverse biased. Okay. C says figure 8.3 shows a circuit symbol of an electronic component. State the difference between the two circuit components in figure 8.1 and figure 8.3. This circuit component is what we call a light dependent resistor. Its resistance increases with increasing light intensity. So as the light intensity increases, its resistance also increases. It's different from the diode. I explained here to say that the circuit component in figure 8.1 does not emit light when current flows through it, whereas the circuit component in figure 8.3 emits light when current flows through it. So this light dependent resistor here will emit light when the current flows through it. However, for a diode, this diode here, it does not emit light when current flows through it.